In part two of this module, we're going to give a few examples of the knowledge and concepts that we have discussed to gain a deeper understanding. So in this example, we have two resistors connected in series, and the two are connected with a third resistor with an unknown value, and the three resistors that are in series is connected to a voltage source of 36 volts. Now, the problem requires us to find the value of the third resistor with an unknown value, with the assumption that the voltage across it, as given by the voltmeter, is 12 volts. Since in this problem, the voltage on one of the resistances that are connected in series is given, which is in this case is 12 volts across the unknown resistance R. It would be fitting to use the concept of voltage divider technique. So according to the formula, the voltage across any resistance on a series connected resistors is equal to the ratio of the resistance of that resistor divided by the total resistance or the equivalent resistance of the uh, series of resistors multiplied by the voltage impressed across the series combination. Since the voltage across R is already given, and that is 12 volts, and then R sub n here would be the resistance R, and the equivalent resistance would be the sum of all resistances, well, using the variable R here, and then the fixed values 2 and 4, and multiplying this ratio by the impressed voltage, which is 36 volts. And from this equation, we can solve for R, which is 3 ohms. Take note that since we already have the value for R, we can now compute for the equivalent resistance of the three resistors, which will give us a value of 9 ohms. Take note that since we already have the equivalent resistance, the voltages across each of the remaining resistances, can also be computed. So for the 2 ohms, that will give us 8 volts. For 4 ohms, that will give us a 6 volts. Take note that I use here also the voltage divider technique. And also note that for a series connected resistors, the sum of the voltages across each of the resistances will be equal to the voltage impressed. So this last line here will serve as a check if our values of the resistances and voltages are correct. In this example, we have two resistors in parallel, 10 and 5 ohms, and the parallel combination is in series with 10 ohms. And the whole thing is connected to a 48 volts supply. Now the problem is asking us what is the current that is flowing through the 5 ohms. So we assigned a variable to that, and that is size of 2. And we also label here the total current that is coming out of the 48 volts as I sub t. So let's go through the solution. So take note that 10 and 5 ohms are in parallel, so therefore we can combine them, and the combination will be in series with the 10 ohms, and therefore that will give us an equivalent resistance of this much. And we can then imagine that the 48 volts is simply connected to this resistance, and we can compute for the total current by simply applying Ohm's law. And for I sub 2, take note that what we have here is two resistors in parallel, and that current is flowing through the parallel combination, which is also I sub t. And in that case, we can apply the current divider technique, which states that I sub 2 will be equals to 10 divided by 10 plus 5, where this 10 here is that 10 there, is two tens, and the ratio is multiplied to whatever current that flows to the parallel combination, which is what we got earlier, which is 3.6, and that will yield a value of 2.4 amperes. In this example, we have three unknown resistances. So two of those resistances are connected in parallel, and their combination is connected in series with another unknown resistor, R sub 1. And this whole thing is connected to a 120 volt source. The value of these resistances are not given. However, the their consumption, their power consumptions are given. So for R sub 1, uh, it absorbs a power of 750 watts. P sub 2 or R sub 2 absorbs 250 watts, and R sub 3 absorbs 200 watts. Now I've indicated here a plus sign for the power, signifying that this power is being absorbed by the resistances. If we total the power that is absorbed by the three unknown resistances, that will give us a power of 1200 watts. Now, take note that resistances do not supply power, they only absorb power, and that power will come from uh, the source, which is 120 volts. So that's why the source here is actually giving out power, and this power can be considered negative power with respect to the source. So, the problem asks us to determine the resistance of the unknown resistors. So the first step here is first to assume an equivalent resistance for all of the resistors. So assume that the 120 volts is simply connected to a single resistance, which is the equivalent resistance of the three resistors. Well, we cannot compute that equivalent resistance because we don't have yet the values of the resistances. We simply assume that the 120 volts is connected to an equivalent resistance. Now, take note that this equivalent resistance is directly connected to the source, so that makes the voltage across the equivalent resistance equals to 120 as well, and the current that is coming out of the source is also the current that flows through this equivalent resistance. So uh, take note that since the equivalent resistance is the combination of the three resistances, the power that is absorbed by the equivalent resistance should be equals to the sum of the three powers that are absorbed by each of the resistances. So therefore, we have here P of R equivalent must be equals to 1200 as well. And by Ohm's law, we know that that power must equals BI, so 120 I sub T. And from this expression or equation, we can actually solve for I sub T, and that will give us 10 amperes. Now going back to the original drawing, we note that the power absorbed by R sub 1 can be expressed in terms of the current that flows through it, that is also I sub t, and that is given by this. And since that power is given, which is 750 watts, and we already know I sub t, that should give us the value for R sub 1. To get the remaining resistances, now we assume an equivalent resistance for just these two resistors, and assume that we combine them. So we combine the two resistors into resistance labeled as R sub 23. And we note that since this is the combination of the two resistances, the power absorbed by this resistance must be equals to the power absorbed by R sub 2 and R sub 3, and that will give us 450 watts. Now take note also that the current that passes through this equivalent resistance R23 is also I sub t, and therefore we can express this power in terms of the current that will give us I sub t squared R23. And since we already have this one, which is equals to 450, and I sub t is also already given, we can compute for the value of the resistance R23, and that will give us 4.5 ohms. The next step is, uh, since we already know the resistance of R23, and we also know the current that passes through this resistance, we can compute for the voltage across it. Let's call it V sub 23. So that will be the current times the resistance, and that will give us 45 volts. Now, since this R23 is the combination of R23 in the original drawing, this voltage V23 is also this voltage here, which is the voltage across each of these resistances, R2 and R3. And because of that, we now know the voltage across resistances R2 and R3. And we can express the power of their powers in terms of that voltage. So for R sub 2, we know that the power in terms of the voltage is given by this one. And since you already have the power, we can actually compute for R sub 2, and that will give us 8.1. Applying the same principle to R3, we can also determine that resistance. So that will give us this value. In this example, we are to determine the resistance RAB. This is the resistance that we will get if we measure the resistance between this terminal and this terminal. In other words, we're trying to get a single resistance, which is the equivalent resistance of this network of resistors. To determine the equivalent resistance, we need to identify those resistances that are in series and in parallel, and then we combine them. To do that, we need to first know what are the nodes of this network of resistors. So they are actually given here. So here we have node C. This connects 10, 6, 1, and 3 ohms. We have node D, connects 1, the 2, 1 ohms, 4 ohms, and 12 ohms. And here at the bottom, we have node B that connects 3, 12, 4, and 5. Okay, so 1 and 5 ohms here are obviously in series, and that can be combined into 6. Uh, 12 and 4 are in parallel because they are connected to nodes D and B. So therefore, they can be combined in parallel. Uh, Resistance 3 ohms and 6 ohms are also in parallel because they belong to the same node, or they're connected to the same node. So node C and node B, and therefore they can be combined as well. So that will give us a more compact circuit that would look like this. So the 6 ohms here is the combination of 1 and 5 in series. 3 ohms here is the combination of 12 and 4 in parallel. 2 ohms here, combination of 3 ohms and 6 ohms in parallel as well. Uh, the 1 ohm here, we didn't do anything, and it's still here. Now for this new circuit, we observe that now we have 3 ohms and 6 ohms in parallel. We combine that, we get 2 ohms, and that will become in series with this 1 ohm, and that will give us an even more compact circuit that would look like this. And finally, we see that 2 and 3 here are in parallel. We combine that, and that combination will be in series with 10, and that will give us this final result. In this next example, we are tasked to uh, find what is the current that flows through this wire, so that connects this point and this point, and also the voltage across 5 ohms. So let's get over with the solution. Now we notice that these uh, two resistances are in parallel because they are connected to this node and this node. So therefore they can be combined as one resistance equals to 21 ohms, and also that 20 and 5 are in parallel as well because they belong to this node and this node as well. And if combined, that will give us a value of 4 ohms. Now 21 and 4 will be in series, and that will give us 25 ohms, and that should also be the equivalent resistance of this circuit. So that means that the 50 volts is simply connected to a resistance equals to 25 ohms, and that should give us a total current equals to 2 amperes, or 50 divided by 25. So we already have the total current that flows out of the source, and that is 2 amperes. Now let's label the current that flows through each of the resistances there. So we notice that uh, 70 ohms and 30 ohms are in parallel because they are connected to the same nodes, this node and this node. So therefore, we can apply a current divider to determine their currents, I sub 1 and I sub 2. So if you do that, that will give us I sub 1 equals to 0.6. So take note, this is uh, two resistances
that are in parallel and current flows towards those resistances that are in parallel. We can do the same for I sub 2, and that will give us 1.4 amperes. Now likewise, notice that resistances 20 and 5 are also in parallel. They're connected to this node and this node as well. Therefore, we can apply also current divider, only that the current, instead of flowing to the parallel combination, it is flowing out actually, and that is also 2 amperes here. But we can still apply current division in that case. And if we do that, we get this result. So I sub 3 is zero point 0.4 and I sub 4 is 1.6. So given that we already know I sub 4, we can immediately determine what is V sub naught, and that will give us 8 volts. Now for I sub naught, we would need some logic to be able to determine this. Now if we consider this point, for example, this point here, this point, uh, we notice that current I sub 1 is flowing to that point, and current I sub naught and I sub 3 is flowing out of that point. So we can say here that the amount of current that flows towards that point must equal to all the currents that flows out of that point. Why is that so? Take note that current is the flow of charges. So that means that the amount of charge that flows towards this point is equal to the charges that flows out of the point. And if that is not true, then charges would accumulate on this point, and that would not be a good thing. So we can say therefore that I sub 1 must equal to the sum of I sub 3 and I sub naught. And from this equation, we can determine I sub naught, and that will give us zero point 0.2 amperes. Now take note that we could do the same logic on this point here. So we can say that the current entering this point must equals to the current that leaves that point. So we can say that the sum of I naught and I 2 must equals I sub 4. And from this equation, we can also determine I sub naught, and that will give us the same result. On our next video, we will be dealing with circuits that cannot easily be combined and come up with an equivalent resistance. So identifying which is series or parallel and combining these resistances are not enough to simplify the circuits. So these circuits are what we call delta or pi circuits, and we need to do some transformations to simplify those circuits. So I'll see you in the next video.